the way it was designed, you are not supposed to have any long answers. Each question required perhaps 2, at most 3 lines. But if you have any questions, I suppose you'll make the solutions available sometime at the same website where we have it. Okay. I also wanted to essentially sort of revisit yesterday's tutorial, the second one, when we went to the lab. In my mind, that was a very good idea. I think it was very useful. It basically tells you that measurements are important. It's not all equations. The other thing is, even with, as Professor Guha was saying, even with a very simple experimental setup, there are many different kinds of experiments that one could do, with apparently a very modest investment in the equipment in this case, which is a soil column. So for instance, for the soil column that he was doing, you could easily change the length of the column, do another experiment, and see whether the solute is obeying advection dispersion hypothesis or a stochastic convective hypothesis. We could do that. I had asked Professor Guha whether the glass beads that they had in that porous media or synthetic porous media, if they were solid glass beads. So there was a time when when I was trying to study this, we were doing a lot of experiments. So apart from solid glass beads, it's possible for us to use hollow glass beads. Okay, hollow glass beads, and there are so that means within the sphere it's hollow, and there are very small holes on the surface of the sphere which allow water to go inside this hollow space. And initially you can, with pressure, fill all of these with water also, the hollow space. But they're connected with so fine pores that they don't easily flow out. And if you use those, then that water that is locked in these or within these hollow spheres behaves like immobile water. Okay, and then you can study mobile, immobile water kinds of behavior. Your tailing behavior will be very, very long, because the solute will diffuse into the spheres and it will diffuse out very slowly. So it will take a long time for your entire mass to be recovered at the outlet end. Okay, so just by essentially having a different set of glass beads, same experimental setup, you are essentially able to look at the mobile, immobile behavior as well. Some of the other kinds of experiments which are very interesting that you can do is, it's also possible to take these hollow beads and essentially have them soaked for a very long time in methylene, the dye that you are using, methylene blue, so that inside the sphere, the water is entirely filled with solute at that concentration. And then you can take those beads, put them in clean water, and without adding any more water, without adding any solute at the inlet end, you can start flushing it. So just have clean water go through. And then the solute will diffuse slowly out of these immobile regions, and you'll still get a breakthrough curve, but a different condition. Now initially, in the immobile phase, you have solute throughout the column. And when we do pump and treat kinds of treatments, essentially that is the phenomena we are using. We are essentially pushing a lot of water through the contaminant zone, hoping that some of this contaminant will get attached to the water and come out. Other kinds of experiments that you can do is the same experiment where you have beads which are filled with, let's say, this methylene dye. You can have them only at one location somewhere within the middle of your column and do the same experiment. Observe the breakthrough curve. And then you can ask yourself, with this observation, can I identify where the source was? So source identification is a big problem that we face. We collect some data, we try to find out where the source is. So even in this controlled experiment, you are able to ask yourself, how well do I do with source identification? There are many other things that you can do. Instead of having the source only at one location somewhere in the middle, you can have perhaps one, let's say, in the upstream part of the column, one closer to the downstream part, and then these will act as the source, and now your breakthrough curve will be bimodal. So and again you can apply moment analysis. You'll have to make some modifications, but a whole lot of experiments which I feel offer a lot of insight into solute behavior with very little investment in experimental apparatus. It's not a very expensive thing to do, like you were pointing out. Very modest investment, but it's possible to design a whole slew of experiments which would very nicely complement a contaminant transport course, that could be offered. Okay, but they are the kinds of things that people do. So I thought that was a very good demonstration. He also demonstrated how in the field, essentially you are using packers to sample only from one location in the field, rather than sampling to the entire well. So it's possible therefore to have a screen which allows water only to come in at a certain depth, so you can do depth dependent sampling in the field. Okay. I thought that was all very useful and very, very interesting. So I wanted to follow up on that. Today we'll be talking about moment generating differential equations, and we have mentioned this already. We have talked about this as well in other contexts, but I wanted to perhaps introduce it more formally to you, and also show you or talk to you about some of the very nice things that are possible when we do moment analysis and with these kinds of systems. So to motivate moment generating differential equations, this was a problem that was initially studied by Harvey and Gorelick from Stanford, but now I see that this is fine. Is this what it shows in your notes as well? Okay. So one of the problems I have faced, I guess, is the equations that were prepared long time ago, but I prepared it in PowerPoint version, which is different from the PowerPoint version over here. So in translation, sometimes the equations get messed up. So this doesn't look anything like a 3D is what I'm saying. Okay. Consider 3D advection dispersion equilibrium with non-equilibrium sorption. For it to be 3D, D, V and this X have to be bold. Then that denotes shorthand, vectorial and tensor notation. But the same thing that we talked about earlier, we will assume that the principal axes are aligned with the coordinate axis of the medium, so that the dispersion term only has diagonal terms and so on. So this would be a 3D equation. C would be the concentration in the liquid phase in this notation that Harvey and Gorelick use. Q is the concentration in the phase in the immobile water phase, if you will. Okay, so that the exchange between the mobile and the immobile water concentrations is governed by this difference C minus Q. Okay. And what we do is essentially use a notation where this part d del square c del x square minus v del c del x and all the other terms and other dimensions, all of that is lumped into capital L times c. So it's an operator notation. L times c in one dimension would imply d times d square c dx square minus v times dc dx. If it's three dimensional, you would have the corresponding y and z terms also. Okay. So that if I were to take the Laplace transform of that equation, all the spatial derivatives part would simply become spatial derivatives of the Laplace transform itself. Wherever we have derivatives with time, like del c del t, we would have s times c hat minus the value of c at time t equals 0 according to the Laplace definition. We would get essentially another equation as well from this particular equation. We would combine both of these because we have q hat, but I can find the expression for q hat from this equation, substitute it back, so that I would get an equation, an operator equation in c hat with a certain right hand side. Okay. And for instance, when mu c hat is now the Laplace transform, and therefore if I take its derivative set s equals to 0, I'll get all the moments. Okay. So for the 0th moment, I don't have to take any derivatives. I simply have to set s equal to 0 in this equation, and I get this expression, which basically says, if I'm looking at it in 1D, d del square mu 0 dx square minus v d mu 0 dx should be equal to this, which means I have a differential equation that tells me how mu 0 behaves. So that's why moment generating differential equations. Okay. So we have equations where the unknowns are directly moments. So this was essentially the concept. So let's come to the equation that we have been looking at, and we'll talk about temporal MGDEs first. So PNE CNE model in dimensionless form, that is what we talked about. It's a more general model. It serves as a good sort of a motivating example, if you will. So again, just to remind ourselves, we would have two equations. C1 and C2 would be the dimensionless concentrations, let's say the mobile and the immobile regions. Omega was the Damkohler number, P is Peclet number, R is retardation, beta, if you recall, is the fraction of, let's say, mobile water and mobile sites to the total water content, the total mobile site. So it's a ratio. And in general, you don't have to, but let's say the concentration for the mobile water initially was C10, for the immobile water it's C20, but when we were thinking in terms of probability density functions and so on, we had made this a delta function with an appropriate constant multiplying it so that it would all add up to 1. Okay. Our definitions for mu n, the nth moment, is given like this, and let's think of this as C1. Any concentration would work, but we'll be dealing primarily with C1 as our main variable. So this is our definition for the nth moment for the concentration in the mobile water. Okay, I'm going to define, this is 1D. So sort of following Harvey and Gorelick's idea, I'm going to define LC1, which is my shorthand notation, operator notation for this spatial operator, 1 over p del square C1 del C square minus del C1 del Z. Okay. Then my first equation over here simply is LC1, which is of all of this, should be this term plus this term plus this term. Okay. Now if I take the Laplace transform of this entire equation, this has only spatial derivatives. So the Laplace transform simply transforms to C1 hat. I can take Laplace transform of the derivative, I can do my usual Laplace transforms. I'll take the Laplace transform of the second equation also, so that I can relate the C2 hat that I get over here, use the C2 hat I get from here to substitute back, get this expression on the right hand side. So a little bit of algebra involved. But what we have is then an equation which says d square C1 hat dz square minus dc1 dz equals all of this, but this is now a Laplace transform variable. Okay. Now if this is a Laplace transform variable, now we can do our usual thing. So if I have C1 hat, I can essentially take derivatives of C1 hat with respect to s, set them equal to 0. Notice that since this was all only a spatial part, this will simply translate into a similar operator for the moments. All the derivative with respect to s will have to be done on this side. Okay. So that essentially translates to this. So if I do for the 0th moment, so 0th moment, if I come back over here, essentially the 0th moment means I'm not taking a derivatives, I'm simply setting s equal to 0. So if I set s equal to 0, in this term will simply become L of mu 0 hat, or sorry, L of mu 0. Okay, that's by the definition of the Laplace transform. All these s terms will vanish, and we will get an equation like this, which is the governing differential equation for how the 0th moment is going to be evolving in space, because this is over here we have del square, del square with respect to z, or del with respect to z. So basically, as I keep changing my location along the column, this tells me how the 0th moment is going to change for whatever flux is crossing that location. I can do the same thing now. I could go back to this equation, take the first derivative of everything with respect to s, set it equal to 0. I'll get a second equation. Now it will be in terms of mu1. L is that same spatial operator. And if I do it again, I can get it in terms of mu2. In fact, I can, by the time I do 0, 1 and 2, after 3, I'll have a general form of what that right hand side is going to look like. Okay. And I can see it. Therefore, my general equation that I want to write now is L star. I've called this L star now. L star is defined by this. What I have taken is I have taken this g mu n, which occurs on the right hand side of these equations, because that's also in terms of mu. Notice that the first equation over here has mu 0, second equation has a mu 1, third equation has a mu 2, but the form of this is exactly the same in all of them. So I pull that in my definition of the spatial operator, but make this L star instead of L to indicate that I have this extra term, and then I put everything else in the right hand side. Okay. The value of g then is essentially given by this expression. And then now I choose to set my boundary conditions. Notice that I have put plus to minus infinity. Okay, even for temporal moments, I'm going to introduce solute at time t equals 0 at the center, at my coordinate origin. Everything else I have left it as 0 for now. So now what are the interesting things that we are looking at? Notice that this operator over here actually is always the same. It doesn't depend on n. The nature, So the second derivative term with 1 over p, the first derivative term, and the g part, the unknown is changing but nothing over here is changing. For calculating the nth moment, the only thing that changes is the right hand side. For the 0th moment, I'll get one expression on the right hand side. Once I solve for the 0th moment, this part remains the same. For the first moment, I'll get simply a different right hand side, which will involve the 0th moment now. When I want to do the second moment, after I solve for the first moment, I'll essentially substitute it back. The only thing that changes is the right hand side. Okay. So this is very useful for the kinds of things that, and we will see how that becomes useful, because this now is a linear equation where only the right hand side keeps changing. And now we go back to mathematics and say, there is a very special technique that allows us to do this very easily. Okay. If the right hand side is the only thing that's changing, second order differential equation, the homogeneous part is essentially constant. It's only the right hand side that's changing. So we invoke what is called as Green's functions, because Green's functions allows us to do this very well. What it says is, this is the same equation that we have. What it says is, let's solve this where the right hand side is given by this delta function. Okay. Delta of z minus a. So it's centered at when z equals a, if you have a delta function. And if we solve this in terms of the unknown g star, then this g star is the Green's function. So in other words, this equation, if I substitute g star over here, solve for the right hand side of the delta function, the solution that I get is the Green's function for the problem. Okay. And that I have to do only once. And in this case, I'll get a very simple expression. Okay. How does that help us now? Notice that for any order moment, only the right hand side was changing. Okay. So what Green's function says is, if only the right hand side is changing, this part remains the same. Once I have found the Green's function for any other right hand side, my solution is simply the Green's function convoluted with the right hand side. Okay. So solving that huge differential equation with more and more complicated right hand sides essentially boils down to one simple integration. You will solve, so you put a right hand side, do this integral, get the 0th moment. Once we get the 0th moment, change the right hand side, do this again, get the first moment, second moment, and so on. So much, much, much simpler. Okay. So this is one of the, I guess, the advantages or one of the elegances that we look for in our solution. So all moments of higher orders, I'm not solving any differential equations. All I'm doing is a very simple convolution. What does this actually mean in other instances? We have talked about numerical methods. I think numerical methods, and if you need numerical solutions, they are great. Very good stuff goes on in numerical methods. So let us say we have a very heterogeneous aquifer or very heterogeneous porous medium. So far, we assumed that the velocity and dispersion were not changing in space. Let's say they are changing in space. Okay. What would happen to us, or what would happen if I were to go back in this differential equation? Well, we have non-dimensionalized it. If we had not dimensionalized it, the velocity would be a function of space, dispersion would be a function of space. They would not come out the derivative signs, but we would get an equation where this part would essentially remain a derivative with respect to time. All the spatial variability would be in this part only. So if my velocity is changing with space, dispersion is changing with space, I would have another differential equation. My definition for L would not be this. It would have, del by del z of d, del c, and so on. But it would still be a spatial operator. Everything that I have done so far would essentially go through, only my definition for this part would have changed. I would still get a similar expression for my moments. Okay. So if I wanted to do this, then essentially now I have to perhaps write a numerical code to solve this problem, because I may not have analytical solutions. So if I do finite differences or finite elements, I would set it up. Notice that when we do this, it's only the right hand side that is going to be changing for different moments. So when we set up our matrix of equations, we have matrix A multiplying an unknown equals to a right hand side, right? So that matrix A will essentially be different because we have heterogeneity, so terms will, but that matrix A is not going to change for different moments, because this part is essentially remaining the same. So effectively what that means is, when I solve that system of equations, my matrix A that I am inverting, I have to invert it only once. Okay. Or basically we don't actually invert a matrix, we take its LU decomposition, but the LU decomposition is being done only once. After that, the right hand side changes, you get the 0th moment. Using the 0th moment, change the right hand side, you get the first moment, but you are not inverting that matrix again. Okay. So now we are talking about this in 1D. Imagine you are doing a problem in 3D. So you have essentially a 3D field, very heterogeneous, you have all that characterized. What you are interested in is how much flux is crossing a control plane someplace. You essentially then define that problem in terms of higher order moments, but you can still do the same thing. You would have a much more complicated L function over here. It would be varying in space. 3D system, large, you would be doing only one inversion, once. After that, the only thing that you change is the right hand side. Over here, you basically substitute the right hand side first to get the 0th moment. Based on the 0th moment, you have a new right hand side for the first moment. Based on that, you essentially change the right hand side for the second moment, and so on. One inversion, and you get all moments, that means you are solving this large complicated 3D system of equations only once, as opposed to, let's say if you wanted to do this whole thing numerically, C is going to be varying as a function of t, so you'll be doing this inversion at every time step. You would do however many time steps, you would do all those matrix inversions, you will get C z of t, then you would be integrating all of those in space. None of that is required, one inversion. So that's the nice thing, or what we would say is the elegant thing about linear systems. Okay. So even for heterogeneous problems, only one inversion of the spatial operator, which essentially in this context simply says one Green's function and we are done. The rest of it is very easy, much easier. So if I do this with the Green's function, I can essentially solve for mu0 of z, change the right hand side, solve for mu1 of z, change the right hand side, solve for mu2 of z, and I could keep doing this. And again, you will see that each of these moments that we have are going to depend on beta r. R1 and R2 have been defined over here. They were in terms of p and so on, and the g values. So we the g was, remember, it's over here, which we had defined, and it has all the gamma and omega terms. So nevertheless, we are getting all these expressions for moments in terms of z. That means z is the distance. At any given distance, what is the 0th moment, what is the first moment? We get those fairly easily. Okay. So very nice. So there are a lot of these nice properties that we have for linear systems. Even for very complex heterogeneities, we are able to leverage these kinds of ideas to do our computations. Okay. So when we have an equation like this, notice that the g function over here had these degradation terms. If gamma 1 and gamma 2 are 0, if there is no degradation, g will essentially disappear, which case the characteristic roots of this differential equation will change. Remember, for second order differential equations with constant coefficients, you have to find the characteristic roots, and then based on the nature of those characteristic roots, whether they are both negative, both positive, one real, one imaginary, you get different kinds of solutions. So if this term is not going to be there, your nature of your characteristic equation will change. So for no degradation, you would have a different characteristic equation, but otherwise the same process goes through, and I would get expressions for 0th, first and second moments too. So we have made our lives fairly easy through this particular simplification. So this is also, I think, one of the useful or sort of the cool things that one is able to do by leveraging what we learned perhaps in our BTech classes when we were learning about Green's functions and so on. So very, very nice. Once we have these moments, now we can do our usual thing. We can define mu sub n star, and then we can use our expressions for effective velocity and effective dispersion, and we will get those expressions as well. But now these effective velocities and effective dispersions, they will be determined, or they will be governed, they will be influenced by beta, r, omega, the Damkohler number, the decay rates, and what have you. Okay. So what we would do is take a look at a few simple cases, just like the previous time. For some sets of values, case 1, 2, 3, and 4 are simply different combinations of P, R, beta, and omega. Gamma for now I have simply left it as 0.5. And in some cases, the Peckley number is varying. In some cases, beta and gamma are varying. And you can, you can do this. You can look at some of the results. So what we have over here are dimensionless distance. So that means at a given distance, what the temporal moments are going to be. 0th moment here, the top two panels, first moment, second moment. And the 4 curves that you see are for the 4 different cases for those combination of parameters. And one can study the results and form some conclusions. Panels to the right when you have no degradation. Okay. Panels to the left when you do have degradation. So panels to the right, if you look at this 0th moment, if you have no degradation, basically, and these are moments for the C1 part, only the mobile region. So if you have no degradation, after it sets to equilibrium, some of it is going to be in the mobile region, some of it is going to the immobile region, and that partitioning is dependent on beta. Okay, so depending on the value of beta, you should get a value of beta and it should stay there. If you have degradation, notice that the 0th moment starts very high and they will immediately start falling down because you are losing mass. So 0th moment goes down. Okay. The first moment tells you how far the plume is effectively traveling. Okay. And as time goes on, or in this case as distance goes on, this is the travel time, or your estimate the travel time to that distance. And then like I said, once you have degradation, it completely messes up our idea of what is happening. So I think with degradation there needs to be some more or better analysis done. The first moment rises and then essentially starts to drop. Okay. With degradation. Without degradation, it sort of increases linearly, which is what you would expect. So that is what we said, effective velocity is almost a constant, which means the slope of this line is almost a constant, and therefore it's increasing linearly. With degradation, you'll get very strange behavior. Dimensionless distance, this is second moment, which eventually governs the spread. The dimensionless distance, the spread is going to increase, slowly increase when there is no distance. With distance, that means the further along the column you go and collect your outflow data. But with distance, the second moment is going to be also reducing by dispersion. So the plume wants to spread, but because of degradation, it chops off. The longer it stays in the column, the more mass we lose. So actually the plume starts to shrink, and therefore the second moment starts to actually go down rather than keep increasing. So whatever is our natural intuition, with degradation, all of this breaks down. So degradation is actually quite a complex thing. So effective velocities or effective dispersion, again, panels to the right are for no degradation, and there is a difference in scales. So you should be looking at that. Okay, so with effective velocity, effective dispersion, you essentially get different kinds of results, but degradation does play a role. So you can see that they are quite different. Okay. Any questions? So basically, what we said was we are able to do temporal moments using moment generating differential equations. We essentially have a system where the unknowns in our differential equation are the moments, and they are set up in some clever way so that the right hand side is the only thing that's changing as I want higher and higher order moments, and that makes it very simple. One of the things is, this was perhaps in your exam also, so this is dimensionless distance. All the solute is released at z equals 0 at time t equals 0. Okay. And then the plume, basically, because it's going from minus to plus infinity, the plume is allowed to spread in the negative z direction. But even though the convection is mostly going in the positive x direction, so the plume will spread, but it will also start slowly moving to the right, positive x direction. So if you are measuring something in the negative x direction, you may get some concentration values as the plume spreads back, but it will also spread out or leave that region, and so you'll again have concentrations going down, but you are not sampling the entire mass of the plume. You are just measuring some concentrations. Since the whole plume is not sampled, we are not able to do moment analysis for those locations. So what it effectively means is these results are only meaningful for positive numbers. For anything less than 0, even though mathematically you can compute them, but you cannot have the same interpretation that we assign to moments and probability densities and so on. Okay, any questions? Notice that we did temporal moments, we can essentially do spatial moments in sort of the same fashion. Okay. Again, the same governing differential equation. Now the boundary condition is a little different. Again, in C1 at z equals 0, we are going to induce a mass m. We will define Fourier transforms because we want to do spatial moments now. And we had talked about Fourier transforms. So this is the definition we will use. Again, the 1 over 2 pi, we won't worry about it because, as we were told, we can have that be part of the inverse transform, which we will never visit because we are not going to do inverse transforms. We will just use the Fourier transform and use its moment generating property and simply go to moments. Okay. So we go ahead and do that. And now, since we have C1 and C2 both, we define two moments, C and eta. So the nth moment in C corresponds to C1. The nth moment in terms of eta is the moment for C2. And again, notice that we have used alpha bar instead of omega because omega is almost, always reserved as a Fourier transform variable. Okay. Otherwise, no difference as such. So I can essentially go ahead and do the same thing. Notice that if I take Laplace transforms, use these definitions, and then take the derivatives with respect to the transform variable and set the derivatives equal to 0, L star is now simply this part, C1, the dC1 dt. It uses only that part of the operator. The spatial part, notice, is going to be integrated out in the Laplace transform. Okay. A little bit of algebra, you will get equations like this. What it says is, and this is for the 0th moment, which is a particular case of the general case. So we will look at this. The nth moment for C1 is a differential equation which looks like this. Notice that L of Cn is simply d Cn dt. L of eta n is d eta n dt. Okay. So if I want to compute Cn, it's going to depend on Cn, the differential equation. It will have Cn minus 1, Cn minus 2, and it will have eta n also. So again, that means I have to first solve for n equals 0, then I can solve for n equals 1 because eta minus 1 will essentially, that means n minus 1, I will need the two lower order moments to keep doing this. So for n equals 0, we will have this equation. If n equals 1, notice that this term will drop out, so we don't actually ever get to do C minus 2 and so on. So these have to be solved, but this leads to a coupled ordinary differential equation system, two equations in two unknowns. For some simple cases, you will have analytical solutions. Otherwise, you are stuck with a system of 2 by 2, two differential equations in two unknowns. You can solve for this again, or you can basically say, look, I have two equations, two unknowns. My two unknowns are C and eta, which are spatial moments. But this is derivatives in time, so I can actually apply Laplace transform to the spatial moment to essentially try and solve this. So if I do Laplace transforms, notice that this will become Cn hat, it will have an S term, these will have Cn hat and eta hat. We will get an equation which will allow us to relate eta n hat to Cn hat. We will substitute it back in the first equation after transformation, and we will essentially get equations that we can work with. Okay. So, however, if we do solve for it and we are able to essentially write expressions for them, the problem is the solution that we get is still in terms of the Laplace transform variable. So C sub 0 is the Laplace transform inverse of this, where G sub s is some complicated function of s. Same for C1 and C2 and so on. So now we do have to take Laplace transform inverses to be able to get these spatial moments. And we will not go into, so you can take the Laplace transform or you can solve them numerically. So what you have essentially now is some results again for different cases. So just to give you a feel for what is happening, 0th moment. So these are all 0th moment for the mobile concentration. Okay. So this is a case. This is for case 1, case 2, different set of parameters. And E stands for equilibrium, N stands for non-equilibrium. ED is equilibrium with degradation. ND is non-equilibrium with degradation. So if any of these cases, if it is equilibrium, essentially you start with a mass of 1 and with dimensionless time that should not change. No mass is lost. However, if you have degradation, it will eventually you lose all the mass to degradation. If it's non-equilibrium, essentially it will start with all of it being in, let's say, the C1 phase, but after a certain time it will equilibrate and become a constant. So in this case it's almost 0.3, which means the rest of it is essentially, or 0.3 is how much it's going to be for both the equilibrium and non-equilibrium phases. So there is some partitioning that you will get. And for other parameter cases, you'll have different behaviors. This was for the 0th moment for the mobile concentration. We can do the same thing. Now we have 0th moment for the immobile concentration. We start at 0. Eventually we will collect some in the immobile concentration, and that will also come to an equilibrium after a certain time. Okay. So if it's equilibrium without, if there is no non-equilibrium, there is nothing that's going to be there in the in the C2 phase or in the immobile phase. Okay. We can do the same thing and calculate first moments for the mobile phase. If it's if it's a standard case equilibrium, we should expect a straight line. The slope of it is supposed to tell us how fast the plume is essentially moving. But if we have other things happening, especially degradation, you'll see that those all eventually go down to 0. Okay. And this is again the first moment for the immobile concentration. You can do the let's see, second moment for the mobile concentration, which will tell us about how it spreads. Again, if you look at the equilibrium case, this is what we are familiar with. We expect either the dispersion or the second moment to keep increasing and at a rate higher than time increases. But if you do have degradation, notice that it essentially goes up and then comes down. So degradation does mess what our perception is of how moments should behave. And you could do the same for the immobile concentration also. Okay, so I finished much earlier than usual today. Any questions? I think this is the last slide. I think you're all very tired. All right, any questions first? So I think again the basic thing is when you do moment generating differential equations, we are essentially taking the original equations, doing a transformation so that we end up with differential equations that solve for moments directly. And in this case we are able to use Green's functions, which makes it very easy or very nice to do. The equivalent of that, if you are using a numerical method, means you should be only doing one inversion of whatever heterogeneous medium you have, whatever variability you have in space for the parameters. You will discretize it using finite elements, finite differences, or whatever your favorite numerical method is, and eventually you'll end up with a system which says matrix A times some unknown vector equals the right hand side. Okay. That matrix A does not change as you keep changing the moment. Okay. You change the right hand side, solve for the 0th moment. Once you have the 0th moment, you use that to modify your right hand side. Now your unknown is the first moment. Use the first moment, modify again your right hand side. Now your unknown is the second moment, and you are able to do it. So most of the time that is spent in numerical code is trying to invert this matrix. If you have to do only one inversion, one LU decomposition, after that it is very, very fast. Okay. So that is, I think, one of the nice properties of working with systems of this nature. Okay.
So what information is conveyed by the moments of immobile configuration?
Actually not a whole lot. See, it's more for, I guess, our general use. immobile concentration, so I think that's a good question. It doesn't actually have any immediate physical interpretation, because immobile concentration is simply the concentration in the immobile region, unless you have a specific way of sampling only that concentration in the porous medium. So you have to have a syringe which only taps and draws solution out from the immobile region. There is no way you would know, because what you are getting outside is essentially the mobile concentration coming out. The immobile concentration never comes out of the column. What you collect at the outlet is simply the mobile water. So the mobile concentration, so what you collect is always the C1 part. If you are interested in what happened to the rest of it, then you have to see what is there in the immobile part, and that you have to rely on your model to tell you, because there is no other way to, unless you have a specific way of sampling just the immobile concentration as a function of space. Typically when you do this, you are essentially doing an injection, it's drawing solution, so the injection tip from which the solution is drawing is tapping some volume, which will have both mobile and immobiles mixed, but it will mostly be drawing the solution from the mobile water only. The immobile water by definition is locked up and difficult to get to. So I guess the answer to your question is the immobile thing, we just do it more for completeness, but there is no easy way to assign physical meaning to it. You are not going to collect it at the outlet of your column, or you are not able to get it simply by what is happening at the outlet of the column. If it is a conservative tracer, that means it is you are going to recover all of it. There are no reactions, no decay. You are going to recover all of it at the outlet, but all of that has to become part of the mobile water to come out. And that's a good question. Any other questions? All right, we finished almost a little over 15 minutes earlier today. All right. Well, if you have no questions, I'm going to be here. I'm happy to answer any questions. We have a tea break and a picture and all that planned, so we can try and do that now.